Hi guys, welcome to Learn Electronics Repair. And today we're going to talk about a lot of things. Yeah, a lot of things. And we're going to have a look at this Class D amplifier I've been trying to repair because I've learned a few things from this myself, and I'm thinking maybe some of you guys will probably learn as well. So let's start with something very basic, and this will become clear as we progress. Okay. So what I have on my bench is two LEDs connected to two resistors, okay, and three wires. So these three wires are connected to my bench power supply, 12 volts and 12 volts in series. I'll show you. The circuit I have is like this. I have my power supply, which we can represent like so. Diode, transformer, okay, diode the other way, and the center tap, and then some capacitors. So this is the positive end of the capacitor. This goes to here, and then we have the same again, positive end to here, okay. And then I have attached across this some resistors and LEDs. So we have a resistor, we have a green LED, and we have another resistor, and we have a red LED. Green, red. Okay, so that's the circuit we have. Now this power supply generates dual voltage rails. So this is the positive rail. On mine it's set to plus 12 volts. This is ground. And this is minus 12 volts. This is why the rectifier diodes are pointing in the opposite directions, okay? Of course, there is a primary of the transformer connected to the voltage coming in. This could be the 240 volts AC. Okay, so that's the circuit we have. Now, what I just want to discuss and just get clear is what is the voltage on ground? What is the voltage on ground? Because we generally consider ground to be 0 volts. Okay, but is ground really 0 volts? Well, the answer is that all depends where you're coming from, really. Let me show you. If I connect my black meter lead to ground, the black wire here, and my red meter lead to the red, this is the positive supply, 12 volts, I see 12 volts, okay? If I connect my red lead to here now, the negative supply, I see minus 12 volts. So does that mean that there are 0 volts on this lead? Wow. If we, for example, put the black meter lead here and the red one there on ground, there's not 0 volts on ground. It's got 12 volts on it. Yeah? And that wire has got 24 volts on it. And this is ground. Has this now got 0 volts on? Well, you're probably going to say no. And the reason this doesn't have 0 volts on is because it's connected to the rectifier diode. This is the negative supply. So what this very, very clearly demonstrates in a very simple way is that really there is no such thing as a positive and negative voltage. Voltage is the pressure, if you like, of the electrons, okay, flowing into the circuit. The electron flow is the current, and the potential, the pressure, is the voltage. Okay? It's pressure, electrical pressure, if you like. But the whole point is that volts are not like something that is tangible, that really exists. You can't look, even with a very powerful electron microscope, yeah, and see a volt. A volt is not a physical thing. A volt is just a measurement, and it's the measurement of the potential difference between two points. This is the important thing, the potential difference between 2 points. Okay? And one of those points we consider to be ground. It's just a terminology. Ground, what it really means is our reference point. It's the point from which we take all measurements. Okay? And as you have just seen, if I change the point of reference, so I put my black meter lead here and measure to there, this is now plus 12 volts because this is now 0. Has the voltage here really changed? No, it hasn't. The same electrons are flowing in the same directions with the same pressure against them. Yeah, the difference is just this reference point. And that is extremely simple and yet also extremely important. So what voltage is ground? Is it actually 0 volts? Yeah. Well, we could use an analogy here to think about this, okay? So imagine we talk not about electrical pressure, the potential difference, but we talk about air pressure, okay? So we have a sealed chamber, which is off the edge of the page, and we have attached to it a pump. Yeah, I'll draw it like that. A vacuum pump. Okay, if we think about air pressure, what is it? Well, it's, if you like, the weight or the mass of molecules of air or whatever gas this contains pressing against, in this case, the enclosure. Yeah, so all these molecules and atoms, or combination of both, whizzing around cause the pressure. Air itself has mass because all the molecules and atoms have mass. And when you take a fairly large amount, it adds up to quite a bit, okay? So that's what air pressure is. What's the minimum air pressure we can have? What is 0? Well, 0 is if we pump out of here all of the contents. So all the atoms, all the molecules, everything out of here. Now, there is nothing to push against the sides. There's no molecules moving. There's no mass anymore. So the pressure now is 0. Okay, can you see that? And if we reverse this and pump more gas in here and keep on pumping more, the pressure will increase and increase to the point where the pressure inside is more than the pressure outside because we have atmospheric pressure. So I think you can see that with air or any other gas, we can have a pressure of 0, okay? And we do that by removing all of the air, all the molecules, all the atoms. Now, we may think that ground is what we get if we connect this wire or this lead into the ground. Yeah, we literally stick a big metal rod in the ground and we connect it to it. Will it have a voltage of 0? Well, the other question to ask there is, are there any electrons in the ground? Sure, there's loads of them. So you can't say that the actual voltage of that point is 0. Okay, it could be anything. We could connect from here onto the live wire of our mains. Okay, we could do that. And what would happen if we then come along and we measure from here to here? Well, we'll still see 12 volts because we're still measuring the difference between that point and that point, the potential difference in volts. Okay, it doesn't matter if that has nominally 0 or whether it has 1,000,000 volts on it. The difference between here and here will always be 12, and the difference from here to here is going to be minus 12. So I hope you can see, and maybe tell me that was very convoluted, that potential difference is just relative, and it's up to us when we look at the circuit where to stick this black wire. Okay, and wherever we choose to stick this black wire Whatever we read on our meter will be relative to that, our reference point. Okay, we've got that one out of the way. Let's have a look at this amplifier. And here it is. So this is a Class D amplifier. It has 4 audio channels, 1, 2, 3, 4. You can connect 4 speakers, and it has 4 speaker returns to here, okay? We have 2 large smoothing capacitors here. We have another one there, and we have a transformer. So this is the low voltage side of the amplifier. This is the amplifier and its supply. This is the circuitry which takes the mains voltage and steps it down to a voltage that this uses. This doesn't run at mains voltage, it runs at a lower voltage, okay? So that is our amplifier. These channels can be used in 2 different ways. We can either connect the speaker from one of the outputs of the amplifier to here, speaker return, yeah, this point. So effectively this output of the amplifier is driving or changing the voltage on one end of the speaker, and this point is just at a fixed voltage, okay? Let's say that is at 0 volts. So when the cone of the speaker is in its resting position, we'll have no voltage applied, so this must be 0 as well, or the difference between the two will be 0, which is another way of looking at it, okay? We can drive this point positive or negative with respect to this end, and we can cause the speaker cone to move in or out. That is called single-ended mode when you're driving a speaker, okay? And we have 4 channels, so we can have 4 speakers on here. And they can all be independent of each other. Quadraphonic sound, anybody? Okay. The other way we can use these amplifiers is to connect the speaker from the output of one amplifier to the output of the other amplifier, okay? And we can actually have both amplifiers driving one end of the same speaker at the same time. So what happens in that case? We will invert the audio signal on one of the channels. We'll switch it upside down, okay? So that means that when we feed the same audio signal in to both, one of them is inverted. So as this output is going positive, this one is going negative, okay? And then as this one's coming down, this one's going up. So you can see they're in antiphase. That means that because we're driving both ends of the speaker, one end isn't attached to 0 volts. We can actually drive one end of the speaker up towards the positive supply voltage, the maximum, at the same time as driving the other end towards the negative, okay? And that basically gives us twice as much voltage across the speaker, so we can get more volume out of it. So that's what this thing is. Now, a couple of things you really should know about this that may not be obvious, but when I've finished this, they should be obvious, okay? And this is very important when you want to understand how to test and how to work and how to potentially repair this sort of amplifier, okay? Now, this is one of those situations where a little bit of knowledge can be a dangerous thing, okay? Probably a lot of you are coming at this sort of repair having previously worked on or at least understood your Class AB amplifiers. These are the common type of power amplifiers we had until Class D came along, and they work in different ways, and this is really important. With our Class AB amplifier, our audio amplifier, we have a setup which is basically like this. We will have a transformer, okay, with a center tap. And then, because I forgot to draw it, I'll put it in now, we'll have the rectifier diodes, put it in opposite ways, okay. We'll have our large capacitors, positive because this is the positive supply, to the positive end of the capacitor, to here, and from here okay, the positive end of the other capacitor, because this end is more positive than this end. This is the negative supply, okay, negative. And just like I showed you, this is our reference point. This is what we call ground. So if we measure with our black meter lead here to there, we will see a positive voltage, and from here to here we'll see a negative voltage. You'll notice this capacitor has the positive end up here. Well, as I was just showing you, if we put our black lead here, from here to here will be the positive voltage, and from here to here more. So let's say we're measuring from here to here and we see 45 volts plus, and we measure from here black lead to here, we see minus 45 volts negative. If we instead measured from there, so take this as our reference, we will now see here plus 45 volts, and here we will see plus 90 volts. So you can see the readings we take will be different depending on where we're referencing to. In this sort of circuit, conventionally and sensibly, to make our brains understand it easily, we put our black meter lead here and we call it ground. Okay, does it really mean there's 0 volts on there? Well, no, it depends where you're coming from, as I said. Okay, so that's the power supply for our amplifier, and then we have 2 transistors. I'll just draw them like so. Yes, there will be some resistors in this circuit as well. 1 NPN, 1 PNP. Okay. And from the center of these 2 transistors, we will connect our speaker to ground. Here's our speaker, ground. What's happening now? Well, if this transistor is turned on partially or fully, some or all of the positive voltage will appear at this end of the speaker. Okay, what's the other end of the speaker? Well, it's our point of reference. Let's call it ground. Let's call it 0 volts. Okay, if we switch this transistor off and this one is turned on partially or fully, some of this negative voltage or all of it will appear at this end of the speaker, and at this end, well, this will still be 0 volts. It's fixed to this point. Our reference will call it 0. So by feeding an audio signal and here a sine wave which switches these on and off as it passes either side of 0 volts, the voltage on this end of the speaker will go positive or negative. Yeah, it'll keep switching positive or negative at a frequency depending on the audio signal and an amplitude depending on the audio signal. So imagine when current is flowing this way through the speaker to ground, which is really just the other end of the transformer winding. That's all it is. The speaker cone moves outwards, okay, and when current is flowing from here to here, because this is more positive than that, however you want to look at it, current is flowing that way. So again, it's flowing from one end of the transformer winding to the other, if we class the center tap as being an end, okay. The current now flows the opposite way through the speaker cone, and the speaker cone moves the opposite way, okay. When there's no voltage on here, or rather when the voltage on here is the same as the voltage on there, we call that 0, then this will be 0, then the speaker cone will be in the center. And that's a single-ended class A/B amp. Okay, now we can actually do this another way, as I showed you on that amplifier. I won't draw all this again because it's not necessary for the description, but we have the positive supply, okay, we have the negative supply, and we now use 2 amplifiers. So the first amplifier is connected like that, okay, and the second amplifier is the same. I'll just draw it the other way up because I want to, okay, it's connected like this, okay, And instead of connecting our speaker to ground, we connect our speaker from here to here. And then we feed a signal in such that the signal going into these transistors is this way up. And the signal going into these transistors, it's the same signal, but it's upside down. Okay? Look what's going to happen. With an NPN transistor like these, when the voltage on the base is higher than the emitter, the transistor will switch on. So on this positive half cycle, this transistor will conduct. Okay? It'll conduct. It'll increase the voltage on this end of the speaker. At the same time, on these ones, the voltage of the signal is going downwards. Now with a PNP, the base has to be below the emitter voltage to conduct. So while this one is being turned on here, this one is being turned on here. So the current will flow through the speaker to the negative rail. And that's the direction of flow through our speaker. That way, current. The speaker current moves one way. When we come to the negative half cycle, well, this transistor will switch off because the base is now below the emitter. This one will switch on because the base is below the emitter. This is PNP. NPN. And what will happen is now on the negative half cycle, currents can flow through the speaker into here. Okay, positives and negatives always. And this transistor is also being turned on because while that was going negative, this is going positive. So this one turns on. Okay, this conducts. And current flows that way. So we can see, although I've drawn it rather strangely, that on one half cycle we have, let's do it all in orange, current flowing that way, sorry, that way. And on the other half cycle, can we do this? Let's have a go, one moment. See if this works. Ooh, white on orange, how about that? Yeah, in the other half cycle, current is flowing that way. What's the maximum voltage across our speaker? Well, in this case, this is 0 and this is plus or minus 45. Yeah. In this case, this can go to plus 45 and this can go to minus 45 at the same time. So we get 90 volts. And then the same there. Okay. The speaker now cone is moving twice as far with a bit of poetic license. Now, you've seen me explain this before if you're a regular viewer, but I want you to take something very important from this. And what I want you to take away is this. When there's no audio signal, what is the voltage on this end of the speaker? Okay. In fact, what's the voltage on both ends of the speaker? Well, from our meter probe, our point of reference, the voltage on this end is 0. Okay. With no audio signal, these transistors are both switched off. So the voltage here is also 0 volts. So there's no volts across our speaker. There's 0 on both ends. And if we were to measure with a multimeter from here to here, well, it's the same place, it's 0. And if we were to measure from here to here, it will be 0. Plus or minus, nothing's ever perfect in this world, yeah? But that's what we have. What would happen in the case of this one? Well, the first thing you notice, neither end of the speaker are connected to ground. Okay? Neither end are connecting to ground. But if you were to measure across the speaker, when there's no audio signal, all these transistors are switched off, basically, and there's no voltage across the speaker. There's nothing there. There's no voltage. The same also applies if we were to measure either end of this speaker from ground. So again, our black meter probe on ground, okay, and we measure there or there. We'll try both. What we're going to see here, well, both transistors are off, so we're going to see 0, yeah, and we're going to see 0 there. So not only will we see 0 volts across the speaker, We will see 0 volts on either end of the speaker if we measure from here with no audio input, no signal. Okay, got that. Let's move on. And we're going to move on to the Class D amplifiers. So again, this can be single-ended or it can be a bridge. So once again, we'll draw this. Try to remember to put the diodes in it this time. Okay, so we have positive supply, we have our negative supply, we have our center tap, ground, okay, and then we have 2 capacitors, okay, and we have MOSFETs. So the MOSFETs are in place of these transistors, but in this case it's not NPN and PNP, they're both the same type, and we have one MOSFET connected like so, another one, okay, and we can connect our speaker again from the junction of these to here. Okay, the MOSFETs are connected to a MOSFET driver chip. Okay, and this is connected to a pulse width modulator, PWM, and we modulate the pulse width with the audio signal. Okay, so coming to this is basically an oscillator and the audio. The oscillator is like a sawtooth wave, like so, and we compare the level of the sawtooth with the audio at any given instance, and that will give us a pulse, the width of which is proportional to the level of audio. I made a video about this, by the way. How does PWM work? I'll link it from this one. But that's what we have. What the MOSFET driver does is basically coming out of here are a sequence of pulses going from 0 volts, our reference, to plus whatever volts the chip is running on. And this MOSFET driver makes sure that when the voltage is 0, this MOSFET is switched on and this one is switched off. And when the voltage is plus, this one is switched on and this one is switched off. Okay. It also makes sure that in no circumstances can both MOSFETs be on at the same time. Otherwise, you would just have a short. So that's how it works. There is some filtering in here, by the way. I won't bother to draw it. Doesn't matter for this principle. Because the question I'm going to ask you is, what's the voltage here when we have no input, no audio signal? Well, you might think, just like this one, both the transistors are switched off, both the MOSFETs are switched off, so there's no voltage there. But you would be wrong to some extent, because we need to vary the width of the pulse, okay, depending on whether the signal is going positive or negative. We need to vary the width of the pulse. And if we want the speaker to move in this direction when the audio is going positive, we need to make the pulses wider. Okay, so the higher the voltage here, the wider the pulse. So at this point, for example, you might have a pulse width something like that, and then at the top here you would have a much wider pulse. Okay, and likewise, when the audio signal is going to the negative phase, we want to make the pulse width narrower. So again, when it's a little bit negative, you might have a pulse width is sort of a little bit bigger on the minus side than the plus side, okay, something like that. And when we get towards the peak, we will have a very narrow negative pulse. The frequency doesn't change, by the way. I'm sorry, this is not exactly to scale. It's the width that changes. But that's what you'd have. So we know that when the audio is towards the positive end of the signal, as high as it can get, the pulse is very wide. And when it's at the negative end, the pulse is very narrow. So what's the pulse width when it's in the middle? Well, is it going to surprise you? It's 50%. So even with no signal, the pulse width modulator is running and these MOSFETs are switching on and off equally. Okay, they're not both switched off effectively like these are. And the pulse width is 50%, the duty cycle is 50%. So the voltage here is half of the voltage between here and here. It's 50%. Now, that might make you think, well, if we've got no volts here and we've got half the voltage there, we've got voltage across the speaker. No, remember this is all relative. We could say this is 0 volts and this is minus 45 and this is plus 45, in which case we could say, well, that is actually 0, which is the same as that. But to make it more obvious, we can measure from here. We can measure from here. This is 0, this is now plus 45, and this is now plus 90 with reference to here. So you can see that the voltage here is, in fact, half of the voltage across the rails. Yeah, but they're not switching off, they're switching on and running. Okay, let's look at the bridge. Again, it has two sets of MOSFET drivers, or rather one for each pair of MOSFETs. One pulse width modulated signal coming into both. One is effectively inverted, so as one side is going wider pulses, the other one at the top is going narrower, and vice versa. And in doing so, effectively, as the pulse width here is wider, this one is wider, so the current flows that way. And in the other half cycle, as this one is wider, that one is wider, these go narrower, and the current flows the other way. So it's all doing the same thing. Again, what's the voltage on either end of the speaker? Well, depending on your point of reference, it could either appear to be 0 volts on each end of the speaker, or it could appear to be plus 45 volts on each end of the speaker. And if you were really so committed to do so and put your black light on there, you could have minus 45 on both ends of the speaker. And that's what we would see, depending on where we are measuring from. We would see either minus 45, 0, or plus 45 on both ends of the speaker with no signal. Okay, now let's look at our PCB, because it isn't quite like this. So on our amplifier, you'll see we have 4 large capacitors here and 4 large inductors and 4 sets of these big square capacitors, 4 resistors, a pair of MOSFETs on each channel. These are your 4 identical channels. On the power supply end, we have 2 large electrolytics, which are rated at 2200 microfarad for 100 volts. Okay, you can't as easily see the other one. Yes, you can, it's down there. So these 2 are rated the same as each other, and we'll check in a moment, but we'll find that the negative of this one goes to the positive of that one, or vice versa. And they're in series, okay? Then we have another capacitor here, and this one is 1000 microfarad at 200 volts. Now, you might wonder, what is that capacitor doing? And you'll wonder that until you figure out how this is wired up. So I would assume that what I have here is a plus and minus supply. Okay, so on the transformer, I'll have a plus and a minus once they've gone through the rectifiers, I will say. I'll have a center tap. But if you look at this transformer, we will see if we measure from here to here to here, they're all connected together. But this one isn't. Okay, and again on this side, we measure from here, 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 all connected together. This one isn't, okay? If we measure from the winding to the positive end of this capacitor, this is the positive end, the positive rail. This way round, well, we'll see the capacitor charging up, and it just keeps charging up and charging up, okay? This way round with the positive lead here, we will see the capacitor discharging, going through 0, coming back up, and it stops at 0.41. Okay, so that is a diode junction. That is a rectifier diode. That is this diode that I've drawn here, okay? And also here. That is this diode. The junction of the two capacitors, these two as I mentioned, which is here, negative end of this one to positive end of this one, are connected together, so they're in series, okay? And then the negative end of here, you would expect to be a diode from the other end of the winding, and because it's in the opposite direction, black lead to here, but it reads short. There isn't a diode there, okay? Another thing about this power supply, and I will draw this afterwards, but another thing about this power supply, the other large capacitor, that one, the 200 volt capacitor, well, the positive end of this one is connected to the positive end of the ones in series, okay, and the negative end of this one goes to the negative end of these in series, okay. Another thing about this, again, this point here, speaker ref or speaker return, this is what would be the ground on a single-ended amplifier. Does it connect to our transformer? Because it should connect to the center tap on the transformer. Let's have a look. Doesn't connect to there. Doesn't connect to there. Doesn't connect to here. Doesn't connect to here. Okay. That's interesting, isn't it? Where do the speaker wires go to then? Well, I'll actually show you where the speaker return goes to. It goes to the junction of these two capacitors, the ones in series. It goes to there. That's where it returns to. Not a center tap. There is no center tap. Last thing, I'll just show you the negative supply from the bottom end of the two in series, the 100 volts, or from the bottom end of this 200 volts, doesn't matter, they're connected together, goes to here. This is the big heatsink. All the metalwork is connected to the negative supply rail, okay, and that metalwork at the negative supply rail, well, you can see where the earthing points are on here. It connects to ground because this is bolted to the chassis of the amplifier, and this is the ground lead on the amplifier. So the negative supply rail is connected to ground. This will tell you, should straight away, that what we think is the negative supply rail isn't the negative supply rail. It is our reference point. It is our ground. This power supply is single-sided, just a positive supply. There's only one big rectifier diode, there are not two. In fact, we can see that also. Down here you'll see U101, U102, and next to that is D108, and that is the diode, just one, big one, there isn't another one. The other thing is a transistor down there, okay. This is a switching transistor on the high voltage side. So what we have on our amplifier is not like what I've drawn. Let me show you what we do have. We have a transformer winding. Okay. We have a big rectifier diode here. And we have a big capacitor directly across here. This is the 1000 microfarad 200 volt. Okay. This is our supply. This end, because we need a ground reference, we need to measure from somewhere, yeah? So this end is where we should be sticking our black meter lead. It's connected to ground anyway, I've just shown you that on the PCB. So this is our reference point, there isn't a center tap. We then have two more capacitors. Okay. These are the 2200 microfarad 100 volt. 2200 microfarad 100 volt. I know there will be, I haven't found them, but there will be across these two high value resistors. Connected like so and like so. Okay. These are to balance the voltage between the two capacitors to make sure that they charge to the same voltage and stay charged at the same voltage as each other. It's to prevent one charging more than the other, because when we measure it, we'll find that this supply rail is 150 volts. Okay, and we don't want more than 100 volts appearing across either one or the other of these capacitors. Okay. Where does the speaker connect? How does the amplifier connect? So this is a Class D amp, and I'll draw one of the channels in the single-ended mode, but it isn't really. I'll show you, and I'll tell you what it is. We have our two MOSFETs like this. We have our MOSFET driver. And we have our PWM, okay? And we know this switches these alternately. Yes, there are some resistors in here again. Doesn't matter. And we know that with no audio signal coming in, these will be running at 50% duty cycle each. Okay, 50%. So the voltage here will be half of the supply voltage, 75 volts, okay? And our speaker connects to here via some inductors. Again, I will just show you on the circuit board afterwards. And the other end of that, where does it go? Well, actually, it goes to here. This is that SPK ref, the 4 tabs where you can actually connect your speaker, okay? So our speaker connects across there. Important. When the amplifier is idle and we measure from here to the speaker terminal, will we see 0 volts? No, we'll see 75 volts. And we can't measure from the center tap of here because we don't have one. So we will see 75 volts on this end. And if we measure across our two capacitors, well, they're the same value, it's just a capacitive voltage divider, we will see 75 volts here as well. Because these are switching at such high frequency, the AC, the high frequency, can actually pass through these capacitors. So it still effectively returns the current back to the other end of the transformer. Okay, that's what we have. And this actually is not a single-ended amplifier. This is a half bridge. Okay, that's a half bridge. The same applies on the channels when we put them into bridge mode, like the subwoofer driver on this is. So much the same, plus 150 volts. Speaker connected across the two. Again, with no signal, these are running at 50% duty cycle, so they're always switching. They're all running at 50%. And the voltage here will be, again, with reference to ground, our ground will be plus 75 volts on both ends. So again, the speaker across it has 0, but the output of all the amplifiers, even when, or especially when there is no signal, will be 75. And that is the important thing I wanted you to learn from this video. Because when we come to repair this amplifier, we need to know what to expect and why. And these are the MOSFETs. We have 4 pairs. Each pair is the same. It's identical. These are the MOSFET driver ICs on the other side of the board here. The pulse width modulation for each one comes from this little add-on board. We've had a look on the previous video. We know this comes from an LM319, one for each channel, comparator IC. So, source of here goes to drain of here. Source of this one should go to ground, because it goes to ground on my little schematic. Okay, and drain of this one should go to the positive supply, because it's on my schematic. Yeah, so you can see there, they're wired directly across. And then the speaker terminals, as I mentioned, and I showed you before, go to the junction of these 2 capacitors. Okay, so that's what we have. We have a single-sided power supply. It's not a plus and minus supply. We don't have a center tap on the transformer. This point is not ground. This is where I connected the ground of my scope. Okay. The other 2 outputs on the transformer, by the way, this is your plus and minus 15 volt supply. So all the preamp runs off this supply. Okay. Now you may ask yourself, in fact I asked myself, Rich, when I connected my scope ground to here, and my scope was grounded, and the amplifier is plugged into the mains, and this is ground, effectively what I've done is shorted out that capacitor. There's now ground on both ends of it, so there's 150 volts on this capacitor. Why didn't it explode? Why did that not explode? Well, the reason is quite simple. My workbench is connected to an isolation transformer, or in as much as the socket I plug anything into that I'm working on. Okay, so I have, I'll show it in a minute. I have a big transformer, 240 volts AC, live neutral. Okay, and on the output of this transformer there's also 240 volts, so it doesn't do anything, it doesn't step the voltage up or down, but it isolates it from the mains. Okay, so the mains neutral is connected to ground, we know this. Yeah, on this side of the transformer nothing is connected to ground. So this then goes to a socket, and that's where I plug in anything I want to work on. Yeah, my scope is plugged into a normal main socket, as is all the rest of the equipment on the bench, unless it's battery powered or through something like a USB type power supply. But this scope is grounded. Okay, so when I connected that point to here, I did ground this point, but because of the isolation transformer, this ground is not connected. I'm isolated. It's not connected with either neutral or anything. I am isolated. Okay, also this switch mode transformer, which has a primary, this is your SMPS, that provides isolation as well, even if this was grounded. So basically I didn't short it out, I just made effectively this a reference point of ground. However, something in the circuit noticed that somehow and put the protection lights on. So that's why it didn't blow up, and I'm sure that's also why the protection lights were on. If this had been connected to ground, but there is no ground on my bench, but if this amplifier in the mains lead, so I would have my live and neutral coming here to there, and I would have on my mains lead my yellow and black earth wire coming to there. If I had that on a normal mains lead, on a normal power socket, and my scope is the same, I would have blown something up. This is a very good reason why you should have an isolation transformer. Always. The other reason is that I can touch the live or neutral here and not get a shock, because neither of the wires I'm touching is grounded. Whichever one I touch automatically just becomes ground through me, but no current is flowing. A quick look, guys. So this is down behind my computers. Yeah, that big yellow thing you see down there is my isolation transformer. So this is 2000 VA, effectively about 8 amps, mains in, mains out on that big blue connector over towards the end. I'm sort of shining the light on now, and that big blue connector connects to the variac up here. So this is where I can actually adjust the mains voltage. You can perhaps just see at the moment it says 240 volts on. Okay, turn that down, turn that up. Hopefully you can see that moving. This also shows the current I'm drawing from the power supply, but the isolation transformer has a thermal cutout, so if I get towards the 8 amps it just warms up and shuts down. It's only ever happened once when I was testing some big halogen lighted disco lights, very powerful ones. I had 4 of them on at once and it just tripped the thermal trip, just let it cool down, it was fine. The output of this, and by the way, this, although it's a metal cabinet, isn't grounded, and it has rubber feet, so it doesn't ground through the shelf either, okay? But the output of this via the current limiting light bulb, which is on the top of it, which I can switch in or out if I want, have it direct. And then that comes down to this. So this extension lead, the one with the blue switch, I specifically have one with a blue switch because I know this is the isolated supply, and this is not used for anything other than to power up one device under test. Yeah, it has a few sockets in it, but this is just used for powering up whatever I'm working on, and that way I'm much less likely to get a shock. I hope you enjoyed that. I really do hope you've learned something with that video. Now we can have a look at this amplifier. So when we left this last time, we know that the bridged amplifier, these 2 channels over here, one channel was working. I had audio signal coming out, quite a large voltage of it. The other one was sitting at minus 75 volts. And I said there's something seriously wrong with this amplifier. But I think now the problem was that the reference I was using, which was these, is just not ground. So from there, what I'm going to see, probably half the voltage, 75. So I think the problem with this is not that one of these amplifier channels has like a faulty output device or anything like that, that it's actually shorting the 75 volts to here. And to be quite honest, if it was, the protection lights would come on, and they don't. They go out after it's been powered up for a couple of seconds. I think it's more likely that one of the channels doesn't have any audio signal. So it's pulse width modulating, sitting at 50%, but not changing. So that's why I don't see a signal on that end. I think this is why, with the bass subwoofer connected between the 2, I get very low volume and a kind of a clipping effect. Okay, let's find out in the next video. Ciao for now, guys.